So it's been good to have John sort of put a framework around the unique and evolving understanding that we have between the acute insult and the course of renal recovery or non-recovery. We know that patients that have got acute kidney injury may be able to achieve full recovery, but many patients go on to progressively develop disease with potentially the development of end-stage renal failure. We know that acute kidney injury is a serious and major risk factor, and when people develop acute kidney injury requiring dialysis and are admitted to hospital, if you follow them up for up to 10 years, they have clear, progressive, relentless risk of going on to develop the need for chronic dialysis compared to the control population. And even the patients that have not had the need for acute during their hospital admission are again at almost threefold risk of going on to require chronic dialysis later on. So clearly, acute kidney injury is associated with an increase in the risk of chronic kidney disease. And if you have that kind of association, that also carries an increased risk of mortality, not just the need for dialysis. And if you think this is just a condition, patients that are of older age and got other comorbidities that might predispose them to transform this acute kidney injury into a chronic disease, you have to think again, because this association, this link between the acute insult and the progression of kidney dysfunction to chronic disease is also visible in children. It's been confirmed in multiple studies with an incidence of chronic kidney disease of about 10%, which is very similar to what you see in the adult population. We've looked specifically at patients from the renal trial, patients that have been followed up for 3.5 years after the randomized controlled trial. And in that kind of population, at 3 years, 3.5 years of follow-up, there's a very high incidence not only of renal dysfunction but persistent albumin level, indicating ongoing injury and ongoing abnormalities. You might say that these are patients that have been in intensive care, and of course they would be at risk of having received a much greater injury, and there may be some predisposing factors that have both made them go into intensive care and simultaneously predisposed them to develop chronic kidney disease. AKI is just a manifestation of an underlying condition that predisposes both to AKI and CKD. But this more recent work by the Swedish group led by Max Bell, focusing on patients that had de novo acute kidney injury using Swedish registry data, was able to analyze patients that were presenting to the hospital with acute kidney injury and no evidence of any biochemical abnormalities or renal dysfunction preceding this hospital admission. It's a very patients, almost 100,000 patients, and you can see there that if they develop de novo AKI, of course their survival is immediately impaired, but more relevant to what we're talking about, if you have de novo acute kidney injury, this is a very, very large cohort, and you've had no previous evidence of biochemical renal abnormality, if you follow it up to 3 years, you have a risk of developing chronic kidney disease up to 10-fold incident rate ratio compared to controls. And if you look at the risk of end-stage renal failure, that is almost 20-fold the risk in the general population. So faced with this epidemiologic onslaught of acute kidney injury leading up to chronic kidney disease and end-stage renal failure, there are some logical questions that surely we should ask ourselves. How come these recover and appear to repair themselves, to return to normal function, and some others do not? What are the processes that we associate with this adaptive repair and return to normal function versus perhaps maladaptive repair and failure to return to normal function, development of fibrosis and loss of nephron function. What do we understand about these processes? Well, in order to try to understand how tubules repair themselves, molecular biologists and molecular physiologists have tried to understand a little bit more about the structure of the tubule and where it is that tubular cell repair might be coming from. There's been quite a lot of interest in this concept of scattered epithelial. They appear to be a specific subpopulation of cells that unique morphology, they've got a unique protein expression profile, and they have a greater resistance to injury and greater ability to proliferate. And they can be detected according to special techniques. They appear to represent maybe 2 to 5% of all the cells in the tubules, and they are progenitors of these that can be already identified in the tubular glomerular link as it evolves from the S-shaped body that is the precursor to the glomerulus to the full glomerular structure. So you have these progenitor cells that are scattered around in the tubule and probably amongst the podocytes. And these are the cells that appear to be responsible for much of the regeneration and repair that might take place after injury. You can label these cells, and the nucleus of these cells fluorescent with labeling techniques that use doxycycline. You can see that represented in this cartoon, first showing you the phenotype of these cells as being different from the other cells. They don't have the interdigitated membrane looking onto the lumen of the tubule, and they don't have the basolateral membrane link with the clear organelles, labyrinth-like structures that you see in normal tubular cells. And you can stain them, you can identify them, you can make them fluorescent, and then you can look at what happens when you stimulate their activities by inducing acute kidney injury. And you can see two phenomena take place. One is the phenomenon of the proliferation of these scatter cells, rapidly more resistant to injury, proliferating and repairing the tubules. But also you can see that some tubular cells that were previously not scattered cells de-differentiating themselves back into similar cells, and they themselves also lead to proliferation and repair. However, this proliferation and that activity appears to have two sides to the coin. There is the tubular cell repair component, and there is the component of the cells that surround the glomerulus, because they've got two different potential directions. The podocyte may lead to sclerosis of the glomerulus as their active proliferation, if it's not regulated, just like the tubular cells are seeking to repair the tubules. So what is it that drives or appears to drive the regeneration of the tubules in the right direction or an adaptive direction, and what is it that appears to drive the repair in the wrong direction? All of the animal models suggest that much of this depends on the intensity, but particularly the duration of injury. So that if you have a short burst of injury, there's a greater propensity for the tubular cells to repair themselves, for the nephrons to remain relatively intact, and for the GFR to be preserved. On the other hand, if there is sustained injury, repeated injury, then this appears to be more likely to lead to nephron loss and fibrosis and progressive. So you can have a cartoon like this that summarizes this process. You have a healthy kidney, you have injury to it, you have tubular injury directly, which can be toxic and immunologic, you have endothelial cell activation, you have tubular obstruction, leukocyte recruitment, vascular injury, and then you've got two potential pathways. One is where the macrophages come in and remove the debris in the damaged cells, and they evolve themselves from the M1 phenotype, which is associated with non-fibrotic repair. Then there is resolution of the inflammation, and there's endothelial repair. On the other hand, you can have the impaired repair and fibrosis. So to go a little bit more microscopic, to hone into what the repair and adaptive nature might look like, you have the normal structure with the presence of capillaries and pericytes, endothelial cells, and tubular epithelial cells. Then you have acute kidney injury. With acute kidney injury, you have a degree of necrosis, and you have infiltration with macrophages, which remove the debris and at the same time enable the proliferation of the tubular cells, and at the same time the vascular structures and the pericytes remain intact, and you're able to have full resolution and return to the normal structure. On the other hand, if the injury is sustained or repeated, the repair goes along a different pathway. The macrophages do not undergo the transformation that I was talking about. The pericytes get detached from the vascular wall. There is infiltration of myofibroblasts, and there's the beginning of a fibrotic transformation of the environment in the interstitium and around the vessels, which in turn constricts these vessels and causes a greater risk of ischemia. So what is it that triggers, regulates, transforms all of these activities? As you've heard, it's the immune system, it's the inflammatory response, and people talk about the mechanisms by which this inflammatory response is activated. And of course, irrespective of whether there are pathogens present in the kidney itself, the damage of the kidney tissue releases damage-associated molecular patterns, and they're able to attract macrophages, which are then activated in a very complex orchestra, both manipulation of the cells that are dying and transformation of the biological and molecular activity of the cells that are preserved. You can see in this cartoon some of the things that we understand are taking place, but of course the enormous complexity and the difficulty in understanding and creating a reductionist interpretation of all of this. One of the fascinating things that appear to the reason maladaptive repair is that the tubules appear to repeat the mechanisms associated with aging or senescence. The maladaptive repair that takes place, at least in fibrosis, nephron degeneration, lack of transformation of macrophages, infiltration with myofibroblasts, is very similar to the process of aging. And characteristics that take place with inflammation, such as oxidative stress, DNA damage, mitochondrial injury, appear to recapitulate very, very quickly in an acute way what happens chronically to human beings as part of their senescence. And there are some really interesting characteristics of that process, and one of them is the arrest of the cell cycle during the. So when the cells are injured and the injury is persistent or recurrent, there is the ability or the process leading to a blockage of the cell cycle at the G2 phase. Why does this happen? Why do the cells appear to do this? Well, it appears that this is one prototypical way with which the cells protect their DNA from mutation, from what leads to transformation of the cells into oncogenic cells. And I will return to that phenomenon, which is called mitotic catastrophe, in a minute. But we've got very good experimental evidence, particularly by Joe Bonventure's lab, showing that the nature of the injury will transform the way in which the kidney responds to it. So you've had an acute injury, then you have inflammation, proliferation of tubular cells, and repair. But if you give the same dose 3 times in a row, and every week, and add an insult, then you have a completely different response. You have G2 mitotic arrest, and I'll talk about mitotic catastrophe in a moment. Then with the arrest, there is activation of kinases that signal pro-apoptotic cytokines like transforming growth factor beta. Then that leads to increased fibrosis. And we've got quite good evidence that this is a very important mechanism by which this happens. Why would the cells do this? Cells go down this pathway of fibrosis, cell cycle arrest. And the reason is just like in this phenomenon that recapitulates senescence in an acute situation, they appear to want to avoid mitotic catastrophe. What the hell is mitotic catastrophe, you will say? And that is what happens when there is a significant radical oxygen species, radiation, ultraviolet radiation, or other potential DNA damaging events. And therefore, the cell, by undergoing mitosis in that environment, is continuously exposed to the risk of either DNA fragmentation, chromosomal fragmentation, and the risk of creating cells that are aberrant with abnormal chromosomes and abnormal DNA, which of course exposes it to oncogenesis. And if you had instead the cell cycle arrest, then but the price of preventing that is that you induce tumors, you induce fibrosis, you induce generation of collagen through the release of fibrogenetic factors. And a whole lot of protein cascades are triggered by this initial injury to DNA by radical oxygen species, particularly a variety of proteins of the P group that are involved in controlling the cell cycle. This, we now know, in the clinic, because the cell cycle arrest biomarkers are now the first ones that have been approved by the FDA for the diagnosis of early acute kidney injury. And it all fits in very well with what we now understand about the molecular biology of acute kidney injury and the response of the renal cells to an environment that is DNA damaging. And therefore, it's not surprising that if we look for cell cycle arrest biomarkers, tissue inhibitor metalloproteinase 2 and insulin-like growth factor binding protein 7, you will find them in the urine in this setting. So let me conclude by saying that the molecular biology of adaptive or maladaptive repair is immensely complex and clearly involves intracellular pathways, DNA protection pathways, mitotic pathways, immunological reaction pathways, and cytokine secretion pro-fibrotic pathways. Which of these complex processes that are all simultaneously at work will prevail in a particular patient at a particular time, as best as we can tell, appears to be affected by the injury severity and injury duration. In particular, and this is to me clinically relevant, we believe it's available that injury that is repeated is going to increase the likelihood of fibrotic changes and development of chronic kidney disease. The mechanism of cell cycle arrest is clearly protective and now is of diagnostic value to us. But the clinical implications of what we understand at this time about repair are surely that once somebody develops acute kidney injury, it is imperative that we avoid further injury to the recovering kidney. Thank you very much.